All right. Hello, everyone. This is the March 17th CHL lesson brought to you in part by Hazel, who's very tired. She's like a sack of potatoes right now. So today's lesson is just going to be more practice with Faraday's Law of Induction. So I'm just going to do two example problems. This lesson should only be perhaps maybe 10 minutes, I don't know, 15 minutes. It should be pretty short. Oh, good. We've got 10 people viewing. Hello, everyone. Hello, Steven. Hello, Zach. Hey, Alex. Both Alexes. Hello, Potato Master, which I believe is Justin. Hey, Tim. Hey, Mina. All right. So, yeah. Okay. So, let me just write down Faraday's Law of Induction. I'm going to put her down. So she says hi. And now she's going down. Yesterday we learned Faraday's Law of Induction, which said that the induced EMF, which I called curly E, is equal to minus d flux d time. So the time derivative of the magnetic flux. So induced EMF, this is just another word for voltage or potential difference. Okay, so when you have a loop of wire and it has a magnetic flux going through it, and that flux is changing, then it's going to behave like there's a battery. Even if there is no battery present, it's going to behave like there's a battery in that loop of wire, and it's going to cause current to flow. Okay? Today we're just going to do more example problems, but tomorrow I'll talk about how to determine the actual direction. Okay? Okay. So I'm just going to go right into the examples. So the first example is what if we have a single circular loop of wire has a radius that depends on time. So the radius is r of t equals r naught plus a cosine of omega t. So what does that mean? It means you've got this loop of wire and the radius is actually going like that. So the radius is fluctuating. Someone is asking, can they go to the restroom? That joke's going to get super old. I've already had that joke like 5 times. All right. So yeah, go to the restroom if you need to. Okay, so the radius is changing as time goes on. The radius, or I should say the I'm completely blanking. The magnetic field is perpendicular to the loop. with size, which we will call B. Okay? So what I want to do is I want to go ahead and calculate the induced EMF as a function of time. All right? So the formula, I'm going to start off with the formula for flux. The formula for flux is NB A cosine of theta. So notice how I said a single circular loop. So that means that N equals 1. The magnetic field I called B. So that's B. A, it's a circular loop. So the area of a circular loop is pi r squared. So pi times the quantity r naught plus a cosine of omega t, that squared, times the cosine of theta. Now you might recall that theta is the angle between the magnetic field and the normal to the loop. So anytime the magnetic field is perpendicular to the loop, like it says there, that means that theta equals 0. Okay? So cosine of 0 degrees, which is 1. All right, so my flux is pi b times the quantity r naught plus a cosine of omega t, that quantity squared. All right. So now what I want to do is so that's the flux. Now I want to take the derivative of that. And to do the derivative of this, I'm going to use the chain rule. All right. So this is basically a function within a function, right? So we have pi b, and now I have to take the derivative of this. So I'm going to take the derivative of the outside function. That's going to be 2 r naught plus a cosine of omega t. And then I have to do the derivative of the inside function, which is r naught plus a cosine of omega t. The r naught is a constant. The derivative of cosine is negative sine. And then the chain rule is going to bring out a factor of omega. So we have times negative omega a sine of omega t. All right. So I'm going to simplify this a little bit. And the induced EMF is going to be minus that. So it's going to be minus 2 pi. Oh, there's a double negative. See how there's a negative here? So that's actually going to cancel out that negative and make it a plus. Plus 2 pi omega BA sine of omega t times r naught plus a cosine of omega t. So that's kind of a nasty function. Maybe if you're like me, you're curious, what does that function look like? What does the induced EMF look like as a function of time? Well, guess what, folks? I learned a new trick, and we're going to see what it looks like. So I'm just going to Desmos here. And my internet's a little slow because I'm streaming simultaneously. And let me just type in the functions. So anything that is not time, I'm just going to set equal to 1 because I only care about what does it look like as time goes on. Okay. So we've got on the vertical axis we have induced EMF. And on the horizontal axis we have time. and the function is, so I'm setting everything that is a constant except for time equal to 1. So I have sine of x times 1 plus cosine of x. Right. Let's see. Okay. So this is a graph of what the induced EMF would look like as a function of time. Kind of weird looking, I have to say. I have a question about what does negative induced voltage even mean or tell you. I'm going to talk about that later on, Mr. Elite Pro. I'll talk about that tomorrow. Okay, so we just finished that example. So let's just roll right into the second example. Oh, Zach asked a very good question, which is why was it 0.5 cosine? Just because I wanted the cosine term to be smaller than the 1 here. So that's why. Basically, if the cosine term was too big, if the cosine term is too large, then the radius of the circle just shrinks down to a point, and it's not a circle anymore. You get what I'm saying? So the A is sort of the size of the fluctuation in radius. So it doesn't make sense for the radius to shrink down to 0. Okay? All right. So moving on to the second example here. Let's consider, let me move my papers. Let's consider a circular loop with n turns, has rotational inertia I. A circular loop with n turns has rotational inertia I. It is threaded by a constant magnetic field B. You exert a constant torque tau on the loop. Calculate the induced EMF. All right. So going back to the formula for flux, if I just write it up here, flux is NBA cosine theta. So in yesterday's lesson, I did an example where the magnetic field depended on time. This first example that we did today, you can see that the radius of the loop depended on time. So that's an area that depends on time. In this example, we have a loop that's spinning. It's spinning. So that means the magnetic field is staying in the same direction, but the loop is changing its orientation. So the angle depends on time now, the cosine theta angle. All right? So, I can kind of draw that. You've got the loop, and as a result of the torque, the loop is spinning. okay? And it has a magnetic field that is threading it. So the magnetic field depends on time. Okay? So if we use torque equals I alpha, that's going to tell me the angular acceleration of the loop. So that means that the angular acceleration of the loop is torque over I. Okay? And then you might remember from your angular kinematics equation that delta theta equals omega naught t plus 1/2 alpha t squared. We'll just assume that the loop starts out not spinning. So omega naught is 0. And we just found out what alpha is. So what I get is delta theta is going to be 1/2 times torque over I times t squared. So this is basically our theta as a function of time. So going back to the definition of flux, we can see that the theta is now depending on time. All right, so we're going to have a changing flux. All right, so that means that my flux is NBA cosine theta. I said it's a circular loop, so we'll just say that the area of the loop is A. It doesn't matter, okay? It's just a circle. It's pi r squared, whatever the radius is. And so what really the thing that's changing is the angle. So I have NBA times the cosine of the quantity 1/2 torque over I times t squared. So that's the flux. Now I've got to take the derivative of that to get the induced EMF, negative the derivative. So I do negative, NBA is just a constant. The derivative of cosine is negative sine, which would then cancel out this negative and make it a plus. Okay. But I have to do the chain rule. I have to take the derivative of the inside part, and that's going to give me torque over I times T. Okay? So that's my answer for the induced EMF as a function of time. So once again, switching over to Desmos, we can see what that would look like. You can see that basically we have T, letting all the constants equal 1, we would have T times sine of T squared. So that's your essential functional dependence of this induced EMF. So let me switch over to Desmos. So now I'm just changing the function. So we have T times sine of T squared. Wow, this is crazy looking. So you can see that the induced EMF grows incredibly rapidly. All right. Wow, that's a crazy looking function. Produce some kind of a periodic voltage as a function of time. This is the reason why our power grid is an AC power grid and not a DC power grid. Okay? It's because the way that we produce our power in this country, or the way that we have in the past, is that we've had a loop in a magnetic field and we use some external source of energy to spin on time, okay? Now that might change because pretty soon we're going to have a lot of solar panels. Solar panels produce DC voltages. So AC is just kind of natural because of the way that we produce power currently. But in the future, it might be different. Looks like a... oh, good question. What happens if the induced voltage reaches a really high number or infinity? Okay. It can reach a really high number, and usually what happens is if it reaches a really high number, you'll get sparks jumping across the device. So that's one thing that can happen. For example, you might have heard of hang on, there's some other questions coming in that I'm trying to read. You might have heard of an EMP before. And what an EMP does is it creates this really high changing magnetic field. And then that magnetic field creates huge induced voltages in all of the circuits that are around. And basically, it creates such a huge induced voltage that sparks start jumping between the devices, and it basically fries the electronics. Okay? So that's pretty interesting. The other question was, don't we leave it, or it's more of a statement, don't we leave it as AC since it lets us send the power over lines more easily? So what would the switch to DC power change? So it turns out that we can transmit power using DC with the current technology. It would just require updating our power grid. So yeah, our power lines are designed for AC power. All right, but we do have the technology to do DC when we switch to solar panels. Okay. Just really briefly, one last thing that I wanted to talk about before I sign off is just a third example. I lied. I'm going to do 3 examples. A question. I got 2 really good questions. Awesome. One of them is, when generating electricity, is the magnetic field from just a natural magnetic material? It could be. It could also be electromagnet, so it varies. I think for like those little mini motors that you can buy online, that's from a natural magnetic material. There are all kinds of different motors where, so some of them the magnetic field is produced by an electric arc. Another question is, would you have to use I think you meant the chain rule or the product rule if more than one of the factors were changing in time. The answer is absolutely yes. So if the radius of the loop is changing as time goes on, and the angle is changing as time goes on, then you would have, you'd have to do the chain rule or something like that, or the product. Sign off is, what if you had a graph of the flux versus time? So maybe the flux versus time looks like this. Maybe it looks like a bell curve. All right. And what if I wanted to do a graph of the induced EMF versus time? Okay. So what if I did a graph of the derivative? First of all, the slope is positive here. The slope is negative here. So if you were to do this graph, it kind of looks like this. That's what the derivative looks like. So now if I wanted to see what is the induced EMF as a function of time. The induced EMF is negative the derivative. So I would take my drawing of the derivative and I would flip it upside down to get something. And have him say bye. Bug? He was asleep. So he says bye, and I'll talk to everyone tomorrow.